Hello, this is Atirith. I will be presenting problem number 94 in chapter 5. In this problem, we have an object of mass 1 kilogram that's attached to a cord of length 0.8 meters and travels in a vertical circle whose center is at point O. We've been given that the angle theta that the object makes at that instant with respect to the horizontal line, the dashed horizontal line shown is 30 degrees, and the velocity of the object at that instant in time is 6 meters per second. For the first part of the problem, we want to solve for the tangential acceleration of the object. In order to do that, I've drawn the force diagram appropriate for this object. We have force gravity pulling it down directly downwards, and then we have a force tension that points towards the center of that circle, and this is imposed on the object by the cord. In order to find the tangential acceleration, I've resolved the gravitational force into two components: mg cosine theta, which points in the tangential direction, and mg sine theta, which points in the radial direction, but opposite to force tension. So in order to find the tangential acceleration, we know the force acting in the tangential direction, and by Newton's second law, we know that force over mass is equal to acceleration. So therefore, the tangential acceleration must be the force, which is mg cosine theta, over the mass, which is 1. But you'll note that there's an m in both the numerator and the denominator, so we can cancel them out. So the tangential acceleration would just be g cosine theta, which if we plug the numbers into the calculator, we get 8.48 meters per second squared, or 8.49 meters per second squared, depending on how you choose to round your answer. Now for the second part of the question, we want to find the radial acceleration of the object. And radial acceleration, you'll note, is given by the formula v squared over r, where v is the velocity of the object at that point and r is the radius of the circular path that it takes. So once again, we have the information that we need. We've been given that v is equal to 6 meters per second and r is equal to 0.8 meters. So if we plug these numbers into the formula, we get that the radial acceleration would just be 6 meters per second squared over 0.8 meters, which is equal to 36 meters per second squared over 0.8 meters, which comes out to 45 meters per second squared. Now, for the third part of the problem, they want us to find the force tension that acts on this mass, or acts on this object. So in order to do that, we need to write some of the forces equation in the radial direction. So the sum of the forces in the radial direction, if we take towards the center to be positive, then we have positive force tension along with that negative component of gravity, mg sine theta. So we have sigma F net in the radial direction is equal to force tension plus negative mg sine theta. So force net in the radial direction would be force tension minus mg sine theta because of algebraic reasons. Again, by invoking Newton's second law, we know that acceleration is equal to force over mass. And the acceleration in the radial direction we've already found to be 45 meters per second squared in the previous part of the problem. So knowing these two facts, we can set up an equation A net in the radial direction is equal to force net in the radial direction over the mass, which we know to be 45 meters per second squared. So force net in the radial direction would be 45 meters per second squared times the mass, which is 1 kilogram. And we know force net is equal to force tension minus mg cosine theta. So if we want to find force tension, so we isolate it and we add mg sine theta on the other side, we get force tension is equal to 45 meters per second squared times kilograms plus 9.8 times 1/2, which is mg sine theta. We get 49.9 newtons, and that's our tension force.